All right, our next talk is from Yana. Yana is a PhD student at KU Leuven, working on web security and privacy-related topics. And Yana has a very, very nice and fascinating topic, which is about circumvention of tracking protections by means of CNAME cloaking. We all are probably familiar with circumvention of ad blocking, but of course, when it comes to tracking and anti-tracking, there's a cat and mouse game happening over there as well. So I'm really happy to have Yana as our next speaker. Over to you, Yana.
Hi, well, thank you for having me. So first, let me share my screen. Okay, so I hope you're all able to see my presentation. So then we can get started. I'm sorry. So today I will present our work on CNAME-based tracking, which was our PETS accepted paper this year. And our work was in collaboration with Gunesh from COSIC, Lukasz, an independent researcher, and Wouter and Tom from DistriNet. Okay, so let me first give you a little bit of context. Traditionally, the way third-party tracking works is when a user visits a website that embeds a certain tracker, then a request is sent from the browser to both the server of the website and the tracker then responds with a cookie containing a unique identifier for that user. So in this case, ID is 123. So that cookie is then stored in the browser under the domain of the tracker. And a way to influence the domain under which the cookie is stored is the same site cookie attribute. So the values it can have is strict, lax, or none, and basically it can you can decide with it whether a cookie will be sent only in a first-party context by using the strict attribute, or it is possible to send it cross-origin but same site with a none value. So for instance, with a none value, the cookie would be sent when a request is made to a subdomain of the same website. So the next time that a user visits a different website containing the same tracker, then that same cookie is sent along to the tracker. And that way, the tracker now knows that it was the same user who visited both websites and is able to build a behavioral profile and able to capture the user's interests. So obviously, this poses some privacy problems for us users. So therefore, we have some privacy tools that we can employ to protect ourselves on the web, right? We have, on the one hand, browser extensions. I'm just naming a couple of examples here: Adblock Plus, Ghostery, and Privacy Badger. But we also have built-in browser protections, so anti-tracking tools built in the browsers. And for instance, Safari has its own mechanism called Intelligent Tracking Prevention, which comes down to deleting cookies on websites that the user has not visited for a while. So that makes it harder for the tracker to persistently track the user. Then Firefox has also an anti-tracking tool implemented, and Chrome is mentioned here because while it does not have any by default tracking protection, they are planning on phasing out cookies, third-party cookies, in the future. So of course, there's also other browsers such as Brave and Clicks who also implement their own tracking protection. So on the one hand, we have publisher websites who embed trackers and advertisers on their sites and try to monetize the content that they provide to the users. And on the other hand, we have users who try to protect themselves by employing these tools. So as a reaction to the upcoming tools, trackers themselves try to come up with new ways in order to still be able to track users on the web. So one of those ways is first-party tracking. So this is also meant as a circumvention of cookie blocking. And in this case, the cookie will be set in a first party, so the tracker will only be able to track the user on the same website. And so the limitation of this method is actually that the tracker only gains information on one specific website and is not able to track the user cross-site. So, however, in practice, in combination with persistent tracking, such as fingerprinting, the tracker is in any case able to obtain information about the user across multiple domains. So in our study, we focus on one specific kind of first-party tracking, which is called CNAME-based tracking or CNAME cloaking. And so CNAME refers to a CNAME record, and I will briefly explain what a CNAME record is. So basically, it's a mechanism of DNS which allows for multiple domains to be linked with each other. So in this example, when a user wants to go to the website of facebook.com, but only wants to type fb.com, Facebook would like that the user is redirected to the website of facebook.com. So therefore, it can employ a CNAME record in order to link fb.com with facebook.com, and then the DNS resolver, and that way we'll know that it would eventually have to end up at the correct IP address of facebook.com. So how is this used to track users? Well, in the CNAME-based tracking scenario, a request is sent to a first-party subdomain of the same website. So in this case, the request goes to track.example.com, and a cookie is set, but the cookie will be first-party, and the script is also executed in a first-party context. But if we look at the DNS level, the subdomain of the website is connected with an actual third-party domain of the tracker with the CNAME record. So in essence, the tracker is cloaking itself as being a first-party tracker, or just a first-party domain in general. So how can we detect CNAME-based tracking? Well, we need CNAME records, and not just any CNAME records, but first-party CNAME records pointing to a third party. So in our example, that would be tracker.example.com towards x.tracker.com. For our analysis, we used the public dataset of HTTP Archive, which contains millions of the most frequently visited websites from the Chrome User Experience Report. And from that dataset, we retain first-party requests to a subdomain of that site. So again, in our example, we would look for example.com request to tracker.example.com. So if we combine these two steps, we obtain a list of CNAME tracker candidates. But because not all services that use CNAME records and specifically have a unique subdomain per customer are used for tracking, so for instance, a CDN works in the same way, we have to perform an additional step where we filter out the candidates that are actually tracking. For this, we performed a manual analysis. So we looked up each of the websites of the candidate trackers and referred to their documentation and had a look at whether they were mentioning some services that required analytics or if they were providing some kind of tracking. So after this step, we obtained a list of 13 manually verified trackers. And for each of these trackers, we constructed a tracker-specific fingerprint, which allows us to distinguish the tracking requests from all other traffic. In the last part of our analysis, we ran an additional crawl on a different user agent, so this time Safari, and we found that there was one tracker that was only tracking Safari users. So because the recent change in Safari's policy to use intelligent tracking prevention, there was one tracker that was specifically branding itself as circumventing that protection mechanism. So in this table, I sum up our results, so the 13 different trackers that we found, along with the detected number of publisher websites using the trackers. However, this is a lower bound because if we look at the estimated total number of publishers by using reverse DNS, we find a much larger number. We noted the pricing of the service, if it was available on the website of the tracker. And finally, we had a look at whether the uBlock origin extension on Firefox and Chrome was able to block requests by these trackers and whether these trackers were included in the next DNS CNAME block list. And this block list we also used to extend all of the trackers that we considered in our analysis. So it is important to note that there is a difference between the implementation of uBlock Origin on Firefox and on Chrome, and this is due to the fact that on Firefox, uBlock Origin has implemented a defense against CNAME-based tracking at DNS level by accessing the DNS API in Firefox, and this is technically impossible in Chrome because of the limitations. There is no access to the DNS API in Chrome. Furthermore, 3 of the largest trackers that we found in our analysis were not present in the CNAME block list, which would indicate that our methodology allows us to identify previously unknown trackers. We also had a look at the popularity of the publisher websites that use CNAME-based tracking according to their Tranco rank. And we clearly see that it is heavily biased towards very popular websites. So almost 10% of the top 10,000 most visited websites contain a CNAME-based tracker. We also examined the categories of the publisher websites that use CNAME-based tracking. And as a baseline, we take the distribution of categories of the Tranco top 10,000 most visited websites. And here we also see that the CNAME-based publishers are very biased towards business websites, which could explain their incentive to monetize the content of users. So to sum up, in our study, we found more than 10,000 publisher websites using CNAME-based tracking, 10% of which were present in the Tranco top 10,000 most visited websites at the time. We constructed a list of 13 CNAME-based trackers in varying sizes, and some of which were previously unknown to tracker blocking tools. So now that we know how to detect CNAME-based tracking, we also wanted to get a deeper understanding of the evolution of CNAME-based tracking. So for this, we again used the public dataset of HTTP archive, and we used a recursive approach where we base the amount of CNAME-based tracking in the current month on the amount of CNAME-based tracking in the previous month. So this table shows our historical analysis results. So we did an analysis between December 2018 and October 2020, so almost 2 years. And so in this graph, same site CNAME tracking refers to the CNAME subdomain being first party to the website visited by the user, whereas cross-site means that it was a different website. However, the two domains prove to be related to one another, for instance, by belonging to the same company. So we see over the periods of 2 years that CNAME-based tracking and its popularity is steadily increasing. And we also actually found traces of CNAME-based tracking being used in 2016. So it might have emerged before intelligent tracking prevention was introduced. We also compared the use of third-party tracking with the use of CNAME-based tracking, and for this, we had a look at the evolution of the 10 biggest trackers at the time in the Tranco top 10,000 most visited websites, as well as a random set of smaller trackers. And we see that while the amount of publishers using CNAME-based tracking keeps on increasing, the use of popular trackers remains pretty steady, while the use of smaller trackers declines. And this is actually in line with other studies that have been done recently on the evolution of third-party tracking. We also wanted to have a look specifically at the effects on third-party tracking of CNAME-based tracking. So we performed an evolution. We wanted to look at the evolution of third-party tracking on websites that recently became CNAME publishers. So we looked specifically at websites that were for 6 months not using CNAME-based tracking, then started using it, and then used it for at least 6 more consecutive months. And we found that on those websites, the number of third-party parties did not change, which indicates that the two methods are used on a complementary basis. So either to obtain additional information about the user or to make sure that the user is still being tracked even if he or she has some tracking protection tools. So finally, we evaluated also some privacy and security implications of the CNAME-based tracking scheme. First of all, we found that cookies were leaking. So because the cookies were scoped to the domain of the website, so by using the same site is none attribute, a lot of cookies were being sent to the CNAME subdomain of the tracker. So we had a look at almost 9,000 websites, and we found that at least one cookie was leaking on 95% of them. So in this table, we can see the most common origin of the cookie being set. So for instance, Google Analytics sets first-party cookies on all the websites, and in so many cases, that cookie got sent to the CNAME subdomain. But all these leaks are not per se intentional, but we also had a look at cookies that were leaking in the request URLs. So this practice could indicate cookie syncing, which is also a tracking method that is meant to bypass some tracking protections or to extend the reach of a tracker, because basically the identifying cookie is sent in a request to a different tracker. And we found in our dataset that in a lot of cases, the cookies that were leaking in the request URLs were set by the third-party domain of that same tracker. So this indicates that the tracker was syncing its first-party and third-party domain, making it so bypassing the limitation of CNAME-based tracking, which is that the tracker can only follow the user on one specific website. So we also found some sensitive information that was leaking in cookies. So we did a manual analysis on 50 websites, and on 17 out of the 50 websites, we found at least some information leaking. For instance, in one case, we found the full name of the user, the location, email address, and even in 10 cases, the authentication cookie, which also poses some security issues. And speaking of security issues, we also found that due to the way that the CNAME-based tracking scheme is set up, so because of the fact that the tracker is included in a first-party context with relation to the visited website, we found that two major web security vulnerabilities were possible, which were affecting all of the publisher websites using the tracker. In terms of countermeasures against CNAME-based tracking, so not all browsers have implemented some defense against it. So currently only Brave and Safari have, and they both use a different method. So one of the possibilities would be to do blocking at the DNS level. So to resolve the requests and then look at the full DNS chain and match against it. So this is the method that Brave currently uses. And also, as I mentioned before, uBlock origin on Firefox, not on Chrome. And then, as Andre mentioned in his presentation, there are a couple of more tools who do this by using their DNS data, such as PyTool, AdGuard, and NextDNS. So another method which Safari is using is to, instead of blocking all of the requests to these CNAME trackers, Safari just caps the lifetime of cookies set by these trackers to 7 days, so making it again harder for the trackers to track users persistently. So there are issues definitely with using purely a block list based approach. So without using any DNS data, it would be pretty difficult to keep track of the domains, because first of all, you would need a separate entry in the block list for each customer domain using CNAME-based tracking. So this would be also already a bit of an overhead, and in terms of performance. And furthermore, it is very easy for the tracker to instruct the website to change its subdomain that it uses for CNAME tracking. So it could change it periodically, every week, even randomize it. So it will be very hard to keep track of the changes without any DNS data. So using a DNS level blocking tool is already a very good solution. However, there are possibilities for the trackers to be pushed in other directions that way. For instance, instead of using a CNAME record, the tracker could simply instruct the website to use an A record and connect the subdomain directly with an IP address. And we already found some evidence of this happening in our own data. So it might be in what direction the trackers will go next. So, and then again, the problem arises with if we have to keep track of the IP addresses used by the trackers, then again, performance and efficiency, and it would be easy for the trackers to also use a reverse proxy, for instance. So it goes on. And another direction that they could go in is using name server records instead of CNAME records. So again, so it is important to note that because we are finding defenses, it might push the trackers to do something new that we are not aware of. So we need really to keep a close eye on what the evolution will be and in what direction that the tracking will be going. So to conclude my talk and our study, we used a methodology that allows us to detect previously unknown CNAME-based trackers, so trackers that were previously not known to tracker blocking tools. We performed a large-scale evaluation of CNAME-based tracking, and we found that the popularity of the use of CNAME-based tracking has increased by 21% in the previous 2 years. And finally, we found some serious privacy and security issues that arise from the way that the CNAME scheme is set up. Namely, we found 2 major web security flaws present on websites, and we found that some sensitive information was leaking to the tracker. So that's it. Thank you all for listening, and I'm looking forward to your questions.
Great. Thanks, Yana, for that talk. It's a wealth of information regarding CNAME cloaking. It's just one of those things which is, at the top of everyone's mind, especially anyone who has to do with ad filtering. So this is really, really great. I am going to go into questions from the audience. So the first question is from Tomislav. He says, do you think other extensions adopting uBlock Origin's decloaking approach would be worthwhile? And also, furthermore, would other browsers adopting Firefox's DNS API be worthwhile?
I think that, after having listened to Andrei's talk, I think it would be better if we would have a general approach to block it just at DNS level, instead of having to adapt all these tools that are actually not meant to do all these things, because that could have some cost for efficiency and performance. But it would be better than nothing, of course.
Yeah, that's part of the, it is a bit weird because, as you mentioned, Firefox has the DNS API by which you can sort of like do something, but there are other platforms which don't. So just even having that, capability in those platforms can address this, I think, in important ways.
Yeah.
There's another question. How optimistic are you that we can address the issue of tracking circumvention on a wide scale? It's a pretty general one, but how optimistic are you going into the nitty-gritties of this and seeing this in such detail?
I think that, as I said, it's a bit of a cat and mouse game. So you have to think ahead always. And, deploying tools, of course, helps. But you can never be sure. We can never know that we are blocking all currently known methods of tracking, of course, right? So I think there is still a lot of work to be done in that area.
Yeah. There's another question. Safari's IDP takes a different approach on defense as compared to other vendors or extensions, where they limit the cookie lifetime to 7 days. Mm-hmm. Any thoughts on how to approach? Any thoughts on how effective their approach is compared to other DNS level blocking approaches?
In terms of effectivity, I would think that if the user is actually privacy conscious and does not want to be tracked, it would be definitely more effective to just use a tool that is blocking everything, all requests in the first place. But yeah, I don't know that much about the performance actually of ITP, so it would be interesting to look into.
All right. Those are all the questions that I see in the queue. Once again, Yana, really great to have this talk. If people want to learn more, where should they go?
You can always contact me on Slack or via mail.
All right, you heard it. And once again, thanks, Yana.